Hey guys, one of the most common questions I see on TikTok is people wanting to know what is a tensor product, and I want to try and break it down. Generally, when people take a tensor product, they have kind of two things that live in different universes. Maybe over here we have a vector of latitude and longitude, and over here maybe we have a set of possible velocity vectors. Or maybe we just have 2 bits of data here and 3 bits of data over there, and we want to combine them. Now, there are lots of ways that we could combine them, but if we use a tensor product, we want to think of it as a multiplication. We want to say, hey, put something here on one side, something from the other side on the other, and we want to have rules, like we want to be able to add things together, like vectors, and we want to have this sort of distributive property. Now, there are more rules too, like for instance, there's going to be an implication that anytime you multiply by 0, you should just get whatever the 0 object is in this space. And why might you do this? Well, multiplication can be useful, but also when you take a tensor product of things, you wind up discovering strange relationships between those two objects. For instance, we're all familiar with the clock that has 12 numbers on it. For instance, if I am at 7 p.m. and I add 5 hours, I'm going to get to midnight. But over here, if the clock only had 8 hours, if I was at 7 p.m. and I added 5, I would actually get all the way to the number 4. So you can ask, in these completely different universes, what would happen if we tried to multiply the blue one by the purple one? What would we get? And the point is if we have a multiplication and we have that distributive property, how is that going to impact what the possible answers could be? And the point is that over here, because 1 is the same as 9, right, on that clock with 8 numbers, we can split it up like this, and then we can take each of those 3's and we can break those up as 1 plus 1 plus 1. And so in the end, we're going to get 9 terms here of just 1 times 1. And then we can group together, again by that distributive property, all of those blue ones together. And so even though the blue 1 was not the same as the blue 9, if we tensor that with the purple one, we actually get something the same. Ultimately, this is capturing something about the relationship between 12 and 8. And imagine you had 2 mysterious groups and you were doing these calculations. This information would help you understand maybe what those groups had in common. As an example of something even more severe, if I took that clock with 12 numbers and I did a tensor product of this clock with only 5 numbers, then actually the tensor 1 cross 1, well, 1 is the same as 25 over here. And so I could write this as the sum of 25 things. But when I look at 25 in the other factor, when I use that distributive property, well, now 25 is 0 on the right-hand side. And in fact, if you play this game, it's possible to show that no matter which 2 things you tensor together, it's actually always going to be the same as 1 tensor 0. So this tensor product, although it started with 12 things and 5 things, when you tensor it together, they're actually all equivalent. This tensor product is what we would call trivial. And again, that's detecting some sort of information about the relationship between the numbers 12 and 5, namely that they have no factors in common.